First of all, I would like to introduce myself. My name is Manoj Shikhar. I'm a PMRF scholar at IIT Delhi, and I will be one of the TAs in this course. And about my background, I have done my BTech and MTech from IIT Kharagpur, and currently I'm pursuing my research in the field of continuum mechanics and finite element methods. So the session will go like this. First, I will share one PPT where we will just recapitulate what has been covered in last week. This PPT, like this session is for week 1. So whatever has been covered in the last week, that will be summarized, and after that I will solve some problems, some questions, or I will take some of your doubts. Uh, Before that, I would like to mention one thing that whatever you have got in your assignments, I won't be able to help you with them right now because those are graded assignments, and we are not supposed to help you with that. So whenever you ask any question, I request you not to ask the question which are in the assignments. Okay, so I will share my screen now. So I've already introduced myself. I'm Manoj Shikhar. I have done a BTech and MTech from IIT Kharagpur. I'm a PMRF scholar at Applied Mechanics Department. So this PPT, it will consist of the recapitulation of mathematical concepts, that is vectors and tensors. Then we will discuss traction vector, and then later on we will see the stress tensor and its matrix representation. So what are tensors? They are mathematical objects which we use to represent physical properties. For example, you can write velocity or displacement, or you can write force. Those things are vectors, but essentially they are a special case of tensor. After that, you write stress, or you write mass tensor, density tensor, so on. So one thing about tensor is that it has a rank. Depending upon how many free indices are there, it has a rank. Like suppose if there is one free index in the notation of the tensor, then it has rank 1. So for a scalar, we don't have any free index. That's why the rank will be 0. I will discuss this later on also. And for example, as most of you are reading this solid mechanics, so I assume that you may have done mechanics course. So there you may have encountered stress tensor. So the stress tensor, for stress tensor, we do need 2 free index. So there the rank of the stress tensor or rank of the tensor is second order tensor. One important formula to remember is for a nth rank tensor, we have actually total 3 to the power n coefficients. So for example, if I have a 4th order tensor, so I will have total 3 to the power 4, that is 81 coefficients in its matrix representation. Now we move on to dot product. Most of you have read this in class 12. So you may have read this part like AB cos theta, where A and B are the norm of vectors A and B. And so one thing which is new here is like the dot product can be represented by this matrix multiplication, like A transpose B. And we will see in future that we will use this property extensively when in our further lectures. One more thing to look at it here is that AB cos theta. You can see that here this is the norm of A, norm of B, and this theta it is the angle between those two vectors A and B. So with change in the coordinate system, neither the norm of A will change nor the norm of B will change. Neither the angle between A and B will change. That's why the dot product will be same in any coordinate system. If you think my speed is very high or it is slow, I'd like to have some feedback in between. So you can write in the chat or you can unmute yourself and tell whenever you think the speed is getting off. Now the other product which we already know about is the cross product. So cross product, also known as vector product. Here, okay, Varun. Yeah, Varun, say what doubt do you have? Hello, Varun, you have raised your hand. Do you have any doubt or maybe I have written in chat? So cross product here when we do the cross product of two vectors, we actually get a third vector, and the magnitude of third vector will be a norm of a into norm of b into sine theta, and the direction is this like c. So this is the like unit vector c here. So if I represent a cross b by some vector capital C, so this is how we can write it, and small c will be a unit vector in the direction of capital C. One more thing which I have seen like in earlier when I was doing TATT in offline classes, that students do not use to multiply unit vector in this case. Like they directly used to write AB sine theta. So that is not right. Like if there is a cross product, then you should have a direction also. So you should keep in mind that direction should be there whenever you are writing a cross product. Uh, Also, A cross B vector, whatever we will get, it will be perpendicular to both vectors A and B. This representation we have already seen in BTech first year or before in class 11th or 12th. We can also write cross product as this as a form of a matrix multiplied with a vector. So this matrix is actually a skew symmetric matrix, which we make using the components of vector A. So suppose if it was B cross A, then this would have been a skew symmetric matrix made using components of vector V into vector A, and so on. Also, the vector from which we create this matrix, that vector is actually called axial vector of this skew symmetric matrix. The new kind of product which is getting introduced here is tensor product. So here the first line shows the tensor product of two vectors. So unique thing about this product is that when you do a tensor product between two vectors, you will get a new tensor which will be of higher order. For example, here we are doing tensor product of two vectors, A and B. So we are getting a tensor C which is of second order. Suppose if we had three vectors like A, B, and C, and we were doing the tensor product of them, and we wanted to know what will be the order of the tensor we have formed. Suppose the D tensor is formed, then in that case D will have third order, like it will be a third order tensor. Huh. Now why like while discussing this tensor, there will be a special emphasis on the second order tensor, because we will get it a lot in our studies further in solid mechanics course. We will again and again encounter second order tensors. We will also encounter a fourth order tensor in later part, but second order tensor will be like encountered in every class maybe. So how do you represent the coefficient of a second order tensor like Cij? What is Cij? Cij is the coefficient in the matrix representation of this tensor, capital C. Okay, so how are we making this tensor C? It is A dyadic B. So Ij will be Ai into Bj. So when you write the tensor product, finally you will write it as C equal to A dyadic B. Okay, this sign, this symbol, it is called dyadic product also. So A dyadic product B, and this will be, so you are replacing the vector A here, you're replacing the vector B here, and later on you will get AI bj into EI diatic EJ. Now, the matrix form of tensor changes from coordinate system, but the tensor itself will not change. So you can see that here Cij, Ei, Ej is written. Okay. So in matrix form, these coefficients will have some value. Like for example, let us assume C11 has a value 2. In other coordinate system, suppose we are rotating some coordinates and we are rotating our coordinate system by some 45 degree or 60 degree or whatever angle you want, theta. There, Cij hat will have some value. Let us assume 4 by root 3. So overall, when we calculate the tensor C, it will be same, but the individual components in the matrix form like Cij and Cij hat, they will be different. They may be different. In some cases, they may be equal also, but in general, they will be different. So transpose of a second order tensor is basically the transpose of a matrix. So here you can see I've written A equal to Aij, Ei, Ej. So if we want to write the transpose, it will be Aij, Ej, Ei. So A transpose will be Aji, Ei, Ej. So basically you can write that for a second order tensor, I'm telling, but like keep it in mind because sometimes it happens that for third order tensor also people try to apply this thing, but it is not correct. For second order tensor, you can directly write A transpose as the transpose form of the matrix, which is made using this second order tensor. Now, the product of a second order tensor with first order tensor. So here I'd like to say one thing. There are different kinds of products which will happen. For example, this here, it is a simple, you can consider it as an inner dot product. So C dot B. So when you do a product of second order tensor with a first order tensor, you will actually get a vector. And I hope you remember this symbol delta ij. This is the Kronecker delta function. It has been already discussed in the class if you have gone through your video lectures. So finally, we will get a vector which will be equal to C times B. How do you find the coefficients, this CKL of a second order tensor? For example, here you can see like C is written as C11, C12. So CKL is basically K will go from 1 to 3 and L will also go from 1 to 3, that kind of thing. So how will you find CKL? So you can use this formula directly. CKL is C into EL. So first you will multiply this second order tensor with the first order tensor EL. Then you will take a dot product with EK. So see one thing, when you do this operation, C into EL, you will get a vector. And after that, you will do a dot product of that vector with kth component, like kth direction, I will say, of the Cartesian coordinate. So as an example, here it has been shown that we want to extract C12 from this. So what we will do? CKL. So K is 1, L is 2. So what we will do? We will first multiply this tensor C with E2. Then we will take a dot product with E1. So we will get this C12 component. You can also verify it for rectangular Cartesian coordinate system. You can do it yourself also. Now, how do you multiply two second order tensors? So there are various ways in which two second order tensors can be operated. So first one is like the inner dot product, like the. So here what will happen? You have two tensors A and B. You are taking a dot product, like you're doing an inner dot product, or say it is also called like single contraction. Sorry, this single contraction is different. Like this is an inner dot product. Here, when you do this like A dot B, this is equivalent to multiplying these two matrices, like the matrix forms of these tensors A and B. Now there is a special kind of tensor, rotation tensor. I think somebody has written in the chat, so just give me a second. So rotation tensor are tensors which are related to physical rotation of the object. So for example, if I want to rotate this orthonormal triad E1, E2, E3, I can use a special tensor R, which will just rotate it. It will just rotate the axis. So we can use this formula EI hat, like the final coordinates will be R into EI. Special properties this rotation tensor has is R transpose and R transpose R equal to identity tensor. You can even try it by yourself. I will tell you how do you write a rotation tensor, and determinant of R will be 1. So there is one thing, rotation tensor, they belong to a special kind of uh, sets. Like they belong to orthonormal matrix. Like their matrix representation is actually a orthonormal matrix. So the special property of orthonormal matrix is that it's all the rows and its columns, they are of unit magnitude. For example, this you can see this 100. The magnitude of this column will be 1. Same goes with this and same goes with this. So this is a special. Of course, this is the identity tensor. This means like unit. There is no rotation. If you multiply this with some other coordinate system, you will get the same coordinate system. But anyways, so orthonormal tensors, they have like each of their columns and rows will be of unit magnitude. Each of their rows and columns will be perpendicular to each other, and this property will be followed. Now this determinant of R equal to 1, this is for rotation tensor. Suppose if it was a reflection, then determinant of R will be -1. So for rotation, remember the determinant will be 1. Now in second chapter, so now moving on to what? Hello. Yeah.
Sir, which is a good textbook for this course?
LS Srinath, I think it is written on the site also. There are 2 books.
For GATE also, sir, for GATE preparation.
For GATE preparation, I cannot comment actually. But this is for, you can you can follow these lectures also. I think this will be good enough. But for GATE preparation, you will be needing some special books, I think, because their timing matters a lot. So you need to practice according to that. So,
sir, you are also in this course. You are also teaching example problems of GATE.
No, I won't be teaching the example problems of GATE every now and then. I will be covering whatever questions or whatever like topic our professor will be covering uh, in a week. So I cannot assure you that every week there will be some problems related to GATE. So this course is designed as a solid mechanics course. Maybe some of the GATE syllabus will be covered here. I cannot assure that everything, whatever comes in the GATE will be in this. Okay. For that, I think you can practice separately. Like you can learn the content from here. If you learn this content, I think you will be able to solve the problems in your GATE book, whatever book you will follow.
Thank you, sir.
Yeah, it's okay. What's your name, by the way?
Varun, sir, my name.
Okay, okay, Varun. Okay, so what? So in lecture 2, professor has covered traction. So suppose if we have a solid body, it is fixed here and we are applying some force or some bending moment, whatever different kind of forces or moments you can apply. So this will get deformed. Now, if we cut a section here, like A and B, if we cut a section here and suppose we are considering this part of the body, so with what intensity B is applying force on A? on part A. So that intensity is traction. Now traction will depend upon x and the plane you are taking. So what is x? X is a point. Suppose here I take a point, or I can take a point here. So that traction will depend upon that point, as well as from a point there can be infinite number of planes which can pass. So n is the normal of those planes. So there could be like one plane could pass like this, other plane could pass like this. So traction will also depend upon the uh, normal upon the plane which you are taking. So this thing you should keep in mind. So this derivation has always been already been covered in the class. So this is basically the second law of motion we are applying here. Summation of force external equal to mass into acceleration, and we are substituting the values of contact force and non-contact force. So contact force is generally force by area, and non-contact force is the force by volume. So if you follow the derivation which has been done in the class, you will reach at this formula. Here, the one thing to remember is that though in this figure it is looking that we are having 4 different planes, and this plane CAB, it is not passing through O, but actually it should pass through O. And the way we achieve that is by doing this H equal to 0. So when H tends to 0, this term vanishes. So we finally get this part. From now Ti and Ti minus 1, they are action reaction pair. So T minus I can be replaced by minus of Ti. So when you replace that here, you can see you will get Tn in terms of Ti. So this relation you should remember. Now stress. Now how do we find the stress tensor? So we already have traction vector in this form. What we can do, we can write it as Ei dot n. So if you remember from the dyadic product, this thing like Ti dyadic product with Ei, if you multiply with vector n, it will be of this form. So we can replace Tn by this whole term. So later on, this term will be replaced by, like, because n is common, and it will not be a part of summation. So Tn will be sigma into n. So here one important thing comes out, that the sigma, this stress tensor, is dependent upon the point only. It does not depend upon plane. But our traction vector, it depends upon both point and plane. So this is the recapitulation. Here one thing I will say, that tau 2 means the force is acting on plane with normal in the direction of E1, and the direction of this force is in E2 direction. Similarly, tau 23 is the direction of this shear stress is in E2 direction, but it is acting on a plane which has a normal which is in the E3 direction. So here it will be in minus E3 direction because this is the back face. And so you have to keep one more thing in mind, is that always consider the outer normal of the face. So for this face, outer normal is even. For this face, outer normal is minus even. Similarly, the face at the bottom, at the back, it has normal as minus E3, and the face in the front has normal as E3. So you have to keep this in mind. So this was the recapitulation part. Now I will move on to solve some problems. Is there any doubt? Anyone? If anybody has any doubt, you can ask right now. Otherwise, I will move on to some questions.
The difference between traction and stress.
So traction is the intensity with which like the part we had separated, it will apply force on part A. So traction is a first order tensor. Okay. Stress is a second order tensor. It is not. So traction is basically a first order tensor. It will have a direction also. Stress is a matrix representation. And here, first of all, it is a second order tensor. And the components which we have in this stress tensor, in this stress matrix. Just give me 1 second, I will show you. The components which we have here in this stress matrix. These are formed using different components of tractions in 3 different directions. So those directions should be independent. This has been covered in the class also. So the units are same actually for traction and stress matrix. The units are actually Pascal only. By mistake I told that. But to make a stress matrix, you will need traction in 3 independent directions or 3 independent planes. You need 3 independent planes passing through the same point, and on those 3 independent planes, you need what is the value of traction. So using those components, you will create a matrix representation, and that will be called as stress tensor. Am I audible?
Yes, sir.
Okay. Any other doubt?
Sir, in a plane, traction acts always perpendicular to the plane.
No, traction is not always perpendicular to the plane. Okay. Traction can act in an arbitrary direction. It will have a normal component. It will have a shear component also, like in plane component also. See, suppose I will just do one thing. Let me. So suppose we have a plane like this. Okay, it has a normal. This. So the traction will not be always in the like. Sorry. The traction will not be always like this. This is not true. What will happen? Your plane is defined using normal, right? For definition of plane, you need a normal. This can be the direction of traction. So it will have one normal component, like this will be Tn. Sorry. So to find the normal component, what will you do? You will do T dot n, and this will be other component. I am writing it as Ts, but you consider it as a in plane. Suppose if we know the angle between this, we can find these values. Okay. This will not always act in this direction. This is a misconception many people have. I'm glad you asked it. So, any other doubt?
Sir, then it should be second order tensor also, because it varies in plane and also direction.
No, the order of tensor is defined using some other method. For example, I will show you. So this is a vector. You agree with me up here?
Yes, sir.
Hello? This part. We will look at this only. Okay. How many free indexes are there? Like this I. Only one free index is there, right? Like
Yes, sir.
only this I value can change. Like I can get 1, 2, or 3, whatever it is. Okay. So only I change is able to change freely. So that's why the order of this will be first order tensor. First order tensor. Suppose if I write some matrix C. Look at this part. Here, how many free indices are there? Like I can be choose freely. Like I can be 1, 2, 3. J can also be chosen freely, right? So the order of this tensor will be second order tensor. Now I will give you a tricky question. Suppose if I am writing P equal to Aij into Bij. Can you tell me how many free indices are there here? You will have to look at this complete part. Okay. So here I is coming and here also I is coming. So I is repeating. It is not free anymore. Suppose if I write I equal to 1 here, I will have to write I equal to 1 here also. Similarly, J, if I write J equal to 1 here, I will be forced to write J equal to 1 here. So here no free index is there. No free indices. So what should be the order of tensor here? Bhardwaj, can you reply?
0.
0. So depending upon how many free indices we have, we decide the order of tensor. It is independent of how many variables we need. Okay. So essentially, when we write T as T equal to x comma n, x is a variable, n is a variable, right? This does not decide. These are variables. These are not indices. For example, I will give you a very good example. In maths first year, BTech first year, you may have done function of multiple variables. Okay. For example, this. So here we have two different variables, x and y, but this is a scalar. This is not a vector. This is not a tensor. Because A is a scalar, B is a scalar, and we are assuming x and y is a scalar. So we will finally get what? A scalar value. A scalar value will have zero order. So consider these as variables. These are not, these will not decide how many, like what will be the order of the tensor. Now, if you see this stress tensor sigma, okay, we wrote it as this. But was how many, what do you think? What will be the order of this sigma?
2, sir.
2, right? But how many variables are here?
1.
1. Okay. So I hope you understood what I wanted to say. Okay. So any other doubts, anybody? Okay, then I will move on to solve some problems. Let me drink some water. So the first question, how about I first do the objective questions, then we will move on to the numericals I have prepared. So which of the following statements are true? So I'd like all of you, if you can write in the chat, what do you think? Which of the statements are true? Okay. Nobody is writing, so I'll just say. So the first statement is scalars are zeroth order tensors. This is true. Tensors are independent of coordinate system. This is true. Vectors are more general than tensors. This is false. Vector is one of the cases of tensor. When we have a first order tensor, it is a vector. One can add different tensors of different orders. False. We cannot add two different tensors of different orders. They will have to be of same order. A vector will be added with a vector. A scalar will be added with a scalar. A matrix or a second order tensor will be added with a second order tensor. We cannot add two tensors of different orders. What is the product of a scalar with another vector? So a scalar when multiplied with a vector, it will give a vector only. So the option A is correct. Question 3. Which of the following statements is correct related to the cross product of two vectors? So important points to keep in mind while solving this question. Cross product will give you a vector. So cross product of two vectors gives us a second order tensor. False, because vector is a first order tensor. Cross product of two vectors is same as the product of a skew symmetric tensor formed by the first vector times the second vector. Yeah, this is also true. I showed this skew symmetric matrix which we form using the components of first vector. And the cross product of two vectors is dependent on the coordinate system. This is false. See, one thing to remember is vector is also a tensor. So a vector will remain a vector. Why is this false? I will tell you. A vector will remain a vector irrespective of coordinate system you are choosing. If I have a plane like this and it is pointing in this direction, in any coordinate system, its magnitude, its length will be same, and its direction in which it is pointing will be same. So when you change the coordinate system, what you essentially get is its representation changes, like the form, the column vector with which you will represent this vector, that will be different. Like instead of 1 0 0, it may be 1 by root 2 2 0, something like that. Not 2, 1 by root 2 1 by root 2 0, something like that. But essentially the vector will be same. So when you do a cross B, what is A cross B geometrically? It is the area of that plane. So A cross B will remain, the area will remain the area of that plane, and it will not change depending upon the Cartesian coordinate system. So that's why the third option, cross product of two vectors is dependent on the coordinate system, is false. A second order tensor in general has. So I have shown one formula earlier, 3 to the power n. So for a second order tensor, n will be 2. So you can directly from that formula, you can get that it should have 9 independent coefficients. And you can also see that from here also, like here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the answer will be 9 independent coefficients. Now, question 5, which of the following is false regarding vectors? The representation of vector is different in different coordinate system. This is true. A vector is a second order tensor. False. This one is false. A vector is a first order tensor. True. A vector remains same irrespective of change in the coordinate system. Of course, I discussed it right now only, that the vector will remain whatever it is, irrespective of whatever coordinate system you are taking. Its magnitude will be same. Its direction in which it is pointing will be same. Only the representation, which is the, like you can see in the first line, only this representation will change. Now this question, this is also I have discussed in the PPT. What can we say about the rotation tensor? It uniquely relates a set of 3 orthonormal vectors with another set of 3 orthonormal vectors. True. Any two columns of its matrix form are orthogonal to each other. True. Because this is a rotation tensor is a orthonormal matrix in matrix representation. So all the rows and all the columns, they will be perpendicular to each other. The determinant of a matrix form equals -1, false. If it was reflection, then this will be -1. Otherwise, it is +1. They are second order tensors, true. Rotation tensor is a second order tensor. Its inverse equals its transpose. Its transpose. It is also true. So this is the only false statement. All other are true. 7. Which of the following is a property of rotation tensor? So R transpose will be I. R transpose R will be I. And determinant of R equal to 1. So these three are the properties. This is not correct. This is for if we have asked the property of a reflection tensor. So I've already discussed the MCQ kind of problem you may encounter from lecture 1. Now I will discuss some numericals or some proofs, I will say. So the first question is, question 1. Show that the reason I'm proving this is because in this course later on, you will see this transformation a lot. So that's why I'm showing it to you here, so that in future when sir changes, like sir uses this instead of this directly, you know that why did it happen. So I will show you first using the matrix method. Then I will show you using the index method. Okay. So for any two vectors alpha dot beta, we can write it as alpha transpose into beta. So here also we are taking the RHS. RHS. RHS we have A transpose A dot B. So we will replace it by we can write it like this. Then the product of a matrix with a vector, we can directly write their matrix form, if you remember that. This whole thing transposed with B. Now I'm getting slight lag in my system. So from matrix operations, we know that we can write this thing as A transpose transpose So transpose of a transpose will give us the same matrix. We can write it as A, B. Sorry, should not convert it right now. We will get this. What is this? A transpose into this. These two will form a vector again. A into B. This will form a vector. Because A is a second order tensor, B is a first order tensor. The product of a second order tensor with B will be a vector. So we will essentially get A transpose into A into B. का मतलब हो गया we will get A dot B. So you can see we had to prove A dot AB equal to A transpose A dot B. So this is R equal to LHS. So LHS equal to RHS. Hence proved. Now this is like one of the methods. Why did I show you using matrix method? Is because you already knew how to do matrix operations, how to work with matrices and all. Now I'd show you using the indicial notation method. Okay, so is everything clear till now? Like everybody was able to follow this thing? I should decrease the thickness slightly. Method 2. Using indicial notation. So first we'll take the LHS. Does anybody remember how do we write AB using index notation? So you can see this is the this is how you write a second order tensor using index notation. And we have to multiply it with this vector B. I'm going slow in this class because for you this index notation may be new. For me it was new when I was reading solid mechanics in my third year. So that's why I'm going slow. So here I've already used I, J, and K. So I cannot use these three to write B. It should be something else. So I will write BM, EM. Okay. If you get any doubt in between also, you can ask me. I have no issues. So we can write A dot this will be what? ek.em. So when you multiply this as when you do this inner product, the internal, like this ek, it will get dotted with em. So you will write it as ek.em, and then we will have one for index ej. So finally, this gives us a vector. You can see like we have only one for index ej. And there is one dot product here. So here ei dot ej will have. And we can replace this ekm by delta mk, the Kronecker product. Sorry, the Kronecker delta. This will be delta mk. And we can replace this by delta by g. So this is nothing but, so I will be equal to j. So it should be, it will be replaced by 2. Instead of 4, we will now have only 2 index here. So j. I'm like, you can also write k here and you can write I here. It will not matter. You can write I or m here, because whatever you write here, only those will appear here. So for example, I will show you right now. So you can see j is coming here. The repeating index, they also have a special name. They are also called dummy indices. So j is repeating here, m is repeating here. You could have also written it like this, and there was nothing wrong in it. ai, aik, bk, or this. There is nothing wrong in it. Sorry. There is nothing wrong in writing like this. Only thing you have to remember when you coalesce this, like when you use this delta ij, which will be 1 when I equal to j and 0 when I is not equal to j. At that time, if you are keeping j, like if you are keeping j here, then you should keep j everywhere. Like ai will be replaced by aj. In this case, I kept the index I. That's why I is here and I is there, and j has vanished. J has, like, I could remove j. Now RHS. So here it is A transpose, and here it was A directly. So how do you write a transpose? Can anybody tell me how do you write a transpose? Because I will write it here, of course. So this is how you write a transpose of a matrix or transpose of a second order tensor. I will write directly now because I've already written once. How do you take products? So I will write it here. AKJ AI into EJ EK dot. So can anyone say which index will be coalesced here? Like which index will go with what? From delta ki, which index will go? Like where should I replace? Suppose if I want to keep index I, where in this expression change? Can you please write in the chat? Where should I do that? Since nobody is writing, I will tell. So this delta is ki. So if I want to keep I, wherever there is k in this expression, it will be replaced by I. So, and similarly, wherever there is j in this expression, it will be replaced by m. If I want to keep m. So let's see what I had kept earlier. So our expression will be A, IM, AI, PM. Okay. Here what we have AJ, AJM, BM. Now this dummy index, one of the good things is like we can write it as any other name. Like we can also write it as alpha. I can replace this expression as like this also. A alpha M, A alpha BM. Okay, so just to show you that both the forms are same, like whatever we have got here, this is same. I will replace the alpha by J. So replacing, sorry, I will replace the I by J. Okay, I just did to show you that we can replace the dummy index. We can place dummy indices. Or repeating indices. Repeating indices. Replacing I by J equal to summation of J, summation of M, AJ, AJM, PM. You can see from here, LHS, we have the same expression, AJ, AJM, BM. AJ, AJM, BM. Also see here, I had written, when I kept I and M, I had got AI, AIM, BM. You can see the same expression is here. So with practice, you will be able to do this. It also took a lot of practice for me. Like I think maybe I will say at least one semester to get comfortable with these notations. But if you like whatever I'm doing or whatever like other colleague is doing in his session, if you follow those, you will be able to like deal with these in this course and you will be able to score good marks, I will suggest. So LHS equal to RHS, hence proved. So what I did in this, first I showed you using matrix method because we already know a lot about matrices when we enter engineering. Before that also in 11th, 12th, we already know something about matrix and its transpose and all. Then because we will be following indicial method in the course, I showed you using how to use these indicial methods, how to use this indicial notation, and just to make you comfortable with these indicial notations. If you have any doubt, you can ask in this question right now. This is a really good question and this thing will be appearing a lot. I will tell you, like when you will be dealing with a stress tensor, this thing will be appearing a lot. So this particular question was taken with that mindset only to make you comfortable with this transformation. Anybody has any doubt? So if nobody has any doubt, then I will move on to the next question. Suppose there is a tensor A such that A is a tensor. A is a tensor. We are given A dot E1 is some vector A. A dot E2 is some vector B. And A dot E3 is some vector C. Okay. And the question is, what is the matrix form? Is the matrix form of A in E1, E2, E3 coordinate system? So you can see the beautifulness of this question. It has told you that A is a tensor. And then it is specifically mentioning that you have to give the matrix form of A. It is not telling that if the tensor, write the tensor A. It is telling the write the matrix form of A in E1, E2, E3 coordinate system. So can anybody like comment how do we proceed in this case? So we assume that A has a form like this. So what is given? A dot E1 is A. So we can directly write this thing dot 100. So what is I've already discussed that what will be the expression for a product of a second order tensor with first order tensor? The the matrix form of that tensor into this 1 0 like this other vector, the matrix form of other vector. So it is given A. So we can write A as A1, A2, A3 here. So if you do the matrix multiplication, what you will get? You will get that A11, A21, A31. You will get this from this part equal to A1, A2, A3. Similarly, what should you get if I do this? It will be what? Matrix form of A multiplied with 0, 1, 0 equal to B1, B2, B3. This means we will get the second column now, A12, A22, A23. Sorry, A32. So you will get it as B1, B2, B3. Similarly, A dot E3, I will write it directly here, is C vector. So the third column, A3, A13, A23, A33. You will get it as C1, C2, C3. So we have found our components of this A tensor. We have found the each columns for the matrix representation of this A tensor. So I will just write them all together. A matrix form will be A1, A2, A3, B1, B2, B3, and C1, C2, C3. I hope this is clear to everybody. Anyone has any doubt, they can ask me. Now, if you ask me, sir, where will this be useful? So while going through lecture 3, you may have gone through one example where sir replaced the columns of a stress tensor by the traction vectors, by the components of by the each component of traction vector in a particular direction. The first column vector is replaced by the traction vector in the direction of E1. The traction vector on the plane, which has a normal in the direction of E1. I'm so sorry. So T1 is basically the traction vector on a plane which has normal in the direction E1. Similarly, the second column is replaced by the traction vector on a plane which has a normal in the direction E2 and so on. So there, this is quite useful. You can see it was a similar kind of question. If you replace it by sigma and this by T1, you will be able to see the correlation. Now I will move on to question number 3. Show that A dyadic B we have to show it here. I can show you using both index notation and matrix notation. Which one do you want? Let's first do using matrix method, then we will do using the index method. And the other, this is the first part. The second part is there. It is For this part, I will show you using both matrix and index method. For this, I will just show using matrix method, and you can try yourselves at your home using index method. Okay. So the first question, method 1, matrix method. So the question is, so we take the LHS, let us assume. So LHS will be A dyadic B into C. So in matrix form, what will be there? A B transpose into C. Right. Now, what can you do with this? Now look at this part. Can we replace this by using T transpose into B transpose? Just think about it for a moment. How was I able to write it? I've used a matrix trick here. Like I've used these two properties of matrix. Okay. Transpose of a transpose is the matrix itself. And what is the like AB transpose? It is B transpose A. So this is the transpose of what is written here. And we are taking one more transpose here. So you can see what will happen if you do this thing. It will be B. So here capital B will be replaced by this small one. B transpose into capital A will be replaced by this one. So what will you get? You will get B transpose into C. So I can make this change, right? So LHS will be what? LHS equal to A into C transpose into B whole transpose. Now this could be, this is actually a vector. This thing is actually a vector. Let us denote by this as a D. So we are what? We have AD transpose. Now what is the meaning of AD transpose? It is a dyadic product. So it is a dyadic product of A with D. So LHS is what? Now we will replace D. Like what is D? D was C transpose B. So in this expression, we will replace D. So LHS will be equal to A time, sorry, A into dyadic of C transpose B. This is equal to RHS actually. If you look at the question I had given, equal to RHS, hence proved. Hence proved. Anybody has any doubt till now? If anybody has any doubt till now, you can ask. After this, because I want you to actually prove this second part, but since I don't know if you will be like in the next session, if you will be joining in Friday or on Tuesday. So I will do this question also for you, but using matrix form only. You will have to do this using indicial form on your own. The first part the part 1, I will show you using indicial notation also. Okay, so let's move on then, since none of you are replying. Method 2. Indicial notation. So our LHS was A dyadic B into C. So this is what? AI BJ. I have to follow the solution. Here, I would like to introduce one thing before, like this is not related to this question only. It's called Einstein's summation convention. So according to Einstein's summation convention, for example, this, it is a like and this you will find in many papers actually. We can directly write it as this. We don't need to write this summation symbol. That's why you may have seen that I was writing AI, EI directly. But just give me one second. Sorry. So if it's okay with you, can I use this Einstein summation convention in this further derivation? Because this writing summation every time is just a extra load for me. Generally, whenever I write here, like while doing my research, I prefer to use the Einstein summation convention. This is Einstein summation convention. Okay. Summation convention. One thing to keep in mind is this is followed only when an index, like here m is repeating twice. So it is followed only when an index is getting repeated twice. If you have like, if some index is getting repeated thrice or at 3 places, there you will have to write the summation term. Maybe I will follow this summation, whatever sir is following in class. I just wanted to introduce this one to you. Suppose if you get something in your exam where there is no summation here, you can understand that if this index is repeating here, means it is getting summed. So AI, EI is what basically A1, E1 plus A2, E2 plus A3, E3. So if I write AI, EI sometimes, this also means the same thing. A1, E1 plus A2, E2 plus A3, E3. So it's the same thing. Now we will move on to our proof. I will follow the sir's method only, sir's notation only. So this is, you can see essentially the product of two matrices, but we can replace this by what? Delta JM. Now we will use one trick here. What we will do? So if we prove that this is equal to A transpose B. Oh, sorry. Why am I carrying A here? In question, it was given C, so it should not be A. I'm so sorry. Should be C here, actually. So if we are able to prove that this is C transpose B, our work will be done. It will be because this is A. This is getting diatic with this. So now let's see how do we prove that. So we will expand C transpose B. So C transpose B will be what? C JK EK dot take EJ and B will be what? Yes. So we can write C as C transpose as CJN EN dyadic EJ, and we can write B as something. Let us say I will write let us take P, BP, EP. Okay. So what will be this CJN? Summation of JNP, CJN, BP, EN, EJ dot EP. So what we can do here, we can replace this by delta JP. What does this mean? We can either replace P by J or we can replace J by P. So this will be what? Summation of, I'm keeping J because here we have in the form of J. So I will replace P, CJN, BJ, EN. Can you see these two are same? CJN, BJ, EN. Here also we are getting CJN, BJ, EN. So what we are essentially getting is LHS equal to A dyadic C transpose B, which is equal to RHS. Hence proved. Now, I give you some time to think upon this question. We will have a 5 minutes of break. And after that, we will continue to the second part of this question, which is think about this part right now. How will you solve using this matrix method? Think about the second part of this question. How will you solve using matrix method? You can also see through my solution, which I have already shown you. it will be a similar pattern will be followed. You will like replace this A diadic B by something like A into B transpose, and then we will move on to the solution. So I will give you 5 minutes of break. I will also come in 5 minutes. So So hello students. So the break is over now. 5 minutes are over. I hope you all are at your desk. So now I will be going to the second part of this question. C A dyadic B equal to CA dyadic product into B. Okay, do you want me to show the initial notation method also for the second part? Or will you be able to do it by yourself? You can write in the chat if you want. So matrix method. Let's take LHS only. Now what is this? This is actually C times A. So what can we do? We can write equal to C times A into B transpose. So C times A is also a vector. Let us assume it's a D vector. So DB transpose. So what will be it? D dyadic B. So we replace B by CA, D by CA, sorry. So what we will get? So you can see this is equal to RHS, what we have to prove. So LHS equal to RHS, hence proved. I will show the initial notation also. Let's see. LHS is what? So we'll take all these scalars out. So what are the scalars? Cij are scale, Cij, Ak, and Bl. These are the scalars. Okay. So we have what here? Ei dyadic Ej into Ek dyadic En. What do you think? Which two indices will be coalesced here? These two. So we will get I, J, K, L, Cij, Ak, Bl, EJ dot EK, and we will have EI dyadic EL. So what will happen? This will be Cij AK DL. This will be delta JK. So we can either replace J by K or we can replace K by G into EI dyadic is what? So what can we do here? We can write summation of I, summation of, let us assume we are keeping J, Cij AJ into EI dyadic with LDL DL. Now, if we prove this is same as C into A, what we will get? We will get the RHS. So how to prove this is, these two are same? Simply write A as what will happen? EJ will go with EM. So you should remember this is the, you should directly be able to replace this product. I'm just showing you here so that you know the procedure. EJ dot EM. This is what? Delta JM. I missed an AM here. Just so you can see we are having the same expression here. Cij, AJ, EI. Thus we can replace this by Ca. So what we will get? LHS equal to P into A dyadic B, which is equal to RHS. Hence proved. Anybody has any doubt in like this thing? Anybody has any doubt in converting to initial notation? Okay, so now I will move on to some of the questions from traction. Okay. So first we move on to the numerical question objective question I have. So the first question is how many planes exist at a point in a body? So the answer is infinite. Of course, from a point, you can create any number of planes you want. So traction at a point, question number 2, traction at a point on planes which have oppositely directed normals. Options are A are not related, B are negative of each other due to Newton's second law, are negative of each other due to Newton's third law, are related by acceleration of the body. So the answer is C, are negative of each other due to Newton's third law. The formula to obtain traction on an arbitrary plane at a point requires the following. So what is the formula? This is the formula. Okay. So what do you need? Here n is the normal of that arbitrary plane. So you know information of traction on three. You need to know the information of traction on three planes that are at the same point. Of course, true. If you remember that figure which sir has shown in the class, you will be able to understand this figure. So the planes ABC, COA, OBC, and AOB, they all should pass through the same point. And we are trying to find the traction on the ABC plane. So that's why we did this h equal to 0 to make all the planes going pass through the same point. So the answer is A. We don't need information on planes that are at an adjacent point. No, we don't need it at that plane. We only need at the information which are on the planes which are passing through the same point from which our plane is passing. Magnitude of body force, acceleration of the body. No, we don't need these data also. You can see it from here. While deriving, there is a factor h multiplied here. So when we do h equal to 0, this vanishes. So we don't need data about the mass of the body or acceleration of the body or what is the body force acting on the body. We don't need any data like that. Question 4. Under what condition does the formula Tn summation equal to Tin dot Ei to obtain traction on an arbitrary plane holds? So the first option is only when the body is in a static equilibrium. No, this is equivalent to body, this fourth option, acceleration of the body at that point. It doesn't matter if body is accelerating or not. This formula will hold. Only when no body force is acting. False. This is also not true. Only when the body is not rotating. False. This is also not true. Suppose if the body is rotating also, then also let us assume if we take the centrifugal acceleration, it will also go to 0 because of this h factor. Because instead of a, you will replace using centrifugal acceleration and this h is multiplied here. When you do h equal to 0, this will vanish. So it always holds. So the fourth option is correct. It always holds. Okay, so this question I prepared from lecture 3. The stress tensor at a point in the body is unique. Although there are infinite tractions associated with different planes at that point. Is it true or false? It is true, because the stress tensor, as you saw in the expression, it depends upon the point only. You can see here sigma x into n. So there will be different tractions depending upon different planes you are considering, but the stress tensor at a point will be same. So the answer is true. What can you say about a stress matrix at a point in the body? The first option is stress matrix and stress tensors are same. No, stress matrix actually depends upon the Cartesian like coordinate system. Stress matrix is unique at a point. No, matrix is not unique. Stress tensor is unique. Stress matrix at a point in the body will be different for different coordinate system. So of course, matrix representation will be different. but the tensor will be same. So answer C is correct. Fourth, the diagonal components of a stress matrix represent the normal components of traction on corresponding planes. True. The only first option is true because shear components, they are represented by the off diagonal elements. Sorry. The ith column of the stress matrix in a given coordinate system is the representation of traction on ith coordinate plane in the same coordinate system. Does not have a meaning of its own, will be different. No. The answer is A. The ith column of a stress matrix in a given coordinate system will be the representation of traction on ith coordinate plane. Ith coordinate plane is the plane which has EI as the normal. So is the representation of a traction on ith coordinate plane in the same coordinate system. A is correct. Answer A is correct. Now this is a very good question actually. If you look at question number 6, this, if somebody knows the basics, he or she will be able to solve this within a fraction of a second. What does the following stress matrix represent? So you are given a stress matrix sigma. You can see like there are 3 rows and 3 columns are given. Now the question is, the options are no traction on E3 plane, traction on E2 plane is along E3, normal stress components are all 0. So you can see one thing. What does this column represent? This represent the traction which is on plane which has normal in the direction E3. So basically E3 plane. So you can see that all these 3 are 0. This means that there is no traction on E3 plane. It can also be stated as E3 plane is traction free. Now let us check second part, like the traction on E2 plane is along E3. So what does component of traction mean? Let us assume, let us write here. I will write here. Okay. So let's see, we are writing T as T J I. Or maybe write it like this, T12 T22 T32. So T12 actually means traction on E2 plane along E1 direction. Somebody was asking earlier, sir, if traction will always be perpendicular to the plane. So suppose if this plane is our E2 plane, that means that E2 is our normal of this plane. And this is E1 direction, let us say, and this is third direction E3. So T11 will be along E1. This is T11. Sorry, T12, not T11. I'm so sorry. This is T32. And this is T22. So what is T22? Traction on E2 plane traction on E2 plane along E2 direction. Similarly, T32 is traction along, sorry, on E2 direction. traction on E2 along E3 direction. So in our question, what is given? The second column is what? 0, 0, 1. So this means T32 is non-zero, T12 is 0, and T22 is 0. So traction is non-zero along E3 direction. Let's see if that option is there. So traction on plane E2 is along E3. True. So the part is A and B are true. So this question, I will first do the eighth question, then I will solve this question number 7. And this question is very important. It will clear your doubts. So traction on how many planes are needed to completely define the stress tensor at a point? So we need traction on 3 different planes. So answer is C. Now let us move on to question number 7. Question number 7 says, let me take the data. So what does question number 7 say? Lecture 3, question 7. So we are given a state of stress. We are given state of stress sigma 10, 50, 50. It should be minus 50 actually. Okay, this is state of stress given, and it is asking us to find the value of component of traction on a plane whose normal is n. Okay, we have to find the normal component of the traction. So plane of normal n. So the tricky part which I saw my students to struggle with is they did not divide this vector by its magnitude. You can see that the magnitude of this vector, it is greater than 1. And the normal vector which we write in the traction equation, when we write T equal to sigma n, here it is a unit vector, not any vector along n. Students do this mistake a lot. So first we will have to find what is this n. So what we are given suppose we are given a vector v, which is e1 plus 2e2 plus 3e3. This is the direction of normal. So if we want to find the unit vector normal, what should this be? It should be modulus of v. So what will be this? E1 plus 2e2. And what is norm of v? It will be 1 square plus 2 square plus 3 square. So this is what? This is E1 945. E1 plus 2e2 plus 3e3 by square root of 14. In matrix form, you can write it as 1 by square root of 14. 1, 2, 3. Okay. Find T dot n. So this is what they have asked you. Normal component of traction. Normal component of traction. This is what you need to find. So T is what? Sigma into n. So what is sigma? 10, 50, minus 50, 0, 0, 0, 0, 50, minus 50. Into 1, 2, 3, into 1 by square root of 14. People miss this and they get the wrong answer. So what is this? So let me check if it is minus 50 or not. Should be minus 50 actually. Just let me confirm this. Anyways, I will just solve this problem assuming minus 50 and you would be able to know how to find this. This is the procedure what you will have to follow. So because in question any other matrix can be given, so there is no issue. It will be 50 and this is minus 50 into 1 by root 40. T is what? Minus 40, 50, minus 50 into 1 by root 14. So normal component of traction will be what? T dot n. Normal component of traction. Component of traction. This is what? T transpose into n. So 1 by root 14 into minus 40 plus, sorry, 50 minus 50 into 1, 2, 3, 1 by root 14. We get 1 by 14 here is to multiply minus 40 plus minus 150. So how much this is this? Six point. So this is minus 6.42857, which is equivalent to minus 6.43. So do we have an option there? Yeah, we have an option in A. So option A is correct. I have shown you the way. So here it should be minus 15. Is correct. So what is the method I have followed? We have see the question here. The value of normal component of traction on a plane whose normal is n. The normal component is traction dot n, normal component of that traction. But how do we find that traction? We find using formula T equal to sigma into n. To find n, we first converted this v into a normal, into a unit vector. That's why we divided by the magnitude. We found T. Now we found the normal component of traction. So this is. So thank you everybody for joining. That will be all from my side today. If you have any doubt, you can ask questions now. I hope to see you all on next Tuesday also. Thank you. Thank you, everybody. Anybody has any doubt? Okay, then I will be signing off now. I will be ending this meeting. Thank you.